So I imagine that a lot of you probably already know a lot about the space elevator, but I hope in this introductory talk that I can maybe add a few more details and make it a little bit more interesting for you. So I would like to talk about what is a space elevator, and especially why do we need one? A little bit about the history, the scientific history that is, and then the physical basis for a space elevator, and what do we need to actually build one, and some of the challenges that we're likely to face. And then I'll just spend a little bit of time on what might be the first space elevator. It would be a prototype, and discuss maybe when that could happen. So a space elevator is a way to send payloads into space without rockets. So we use the rotational energy of the Earth and essentially get a free ride. And so we need a tether or a rope of some kind that extends from the surface of the Earth up to and beyond geosynchronous orbit. And then along this tether, you would have climbers, and you all know about climbers, or will soon, that can ascend and descend. And it is likely to be a very high throughput, efficient, and safe system. So this is really probably the only thing that we can think of building right now that would be the basis of an interplanetary transportation infrastructure. And so we have a lot of hopes and for such a structure to be built. Oops. So why do we want one? The Earth's gravity well, of course, is deep, and chemical rockets can really barely get out of it. The rocket equation tells us that we have to spend so much fuel to get a small payload into space, and the deeper into space we go, the less the payload is going to be. And so that's always a problem, always going to be a problem. And because of that, any large space-based projects are very unlikely to be constructed using chemical rockets. So if you want to think about space solar power, settling other planets, things like this, we'll have to have large numbers of even today's heavy lifting rockets. So thousands of launches in a year would be required, and maybe more than that. So it just doesn't seem practical to do anything big in space with rockets. And so we think that the space elevator is probably the best complete solution. So it carries no fuel, beats the rocket equation, so we can get out of the gravity well. And compared to rockets, it's quite low risk. Okay, we don't have the shake and the rattle and the roll of the rockets. We could have much more delicate payloads, and just about anybody could go on a space elevator. You don't have to be an astronaut to do that. And it uses the Earth, of course, to do all the heavy lifting. Now, the first scientific thoughts about space elevators are probably attributed to Tsiolkovsky, and he is said to have got the idea when he visited the Eiffel Tower in 1895, and he thought of a tower that would extend into geosynchronous orbit. Of course, he realized immediately that such a tower would be so massive as to be impractical and wouldn't support itself, but that was the first idea of using the Earth's rotation to put something into orbit. A couple of years later, he derived the rocket equation, okay, which places the ultimate limit on chemical rockets. So in a sense, he had a solution to the rocket equation before he found the problem with rockets. And that's the space elevator. The history, this time a little bit more modern history, begins more or less at 1960. Yuri Artsetonov and Jerome Pearson are credited with independently inventing the modern space elevator. And by modern, I mean a tensile structure instead of a tower. So it's not going to be a heavy iron tower or anything like that. It has to be a tether or a rope. And the modern space elevator concept is based on that. And things started to look really feasible in 1991 with the discovery of carbon nanotubes. So this was the first material ever discovered that was light enough and strong enough to make a space elevator tether possible. And in 2000, Brad Edwards completed the NASA Innovative Advanced Concept Study showing that a space elevator was possible. And if you're interested, there's a book called The Space Elevator in 2002, and that describes his findings. So that is really the basis of what we have been doing recently in space elevator studies and have advanced quite a bit beyond that stage. But he was really the start of the feasible space elevator. In 2000, well, between 2000 and 2004, there were several International Space Elevator Conferences. And this is probably the origin of the International Space Elevator Consortium. And that goes on to this day with the Space Elevator Consortium conferences. 2004, we have a new entry in the strong materials. So now we have another material, graphene, which is strong enough and light enough to serve as a space elevator tether material. And then 2005 through 2009, there was the NASA Centennial Challenge and Space Elevator Games. Actually, this was a series of competitions dealing with climbers and also materials and power beaming. So some basics. Here we have a plot at the bottom of the acceleration on the vertical axis versus the radius, that is the distance from the center of the Earth, of some object, depending on how high up you go. And so starting at the Earth's surface, you have 9.8 meters per second squared. And then as you go outward from the surface, you have a fall off like 1 over r squared, the usual thing. But at a certain altitude, the centrifugal force becomes very significant, and you reach a point where that force equals the gravitational force, and that happens to be geosynchronous orbit. And as you go beyond geosynchronous orbit, now you have achieved basically an effective negative gravity. So basically a 1 over r fall off till you get to geo, and then essentially a linear decrease from there. And so you can sort of see the scale of the structure that we propose to build. Something extending through geosynchronous orbit. Here, the circle represents the magnetopause during the day. So the cable actually extends out into beyond the Earth's magnetosphere. And a very interesting radiation environment exists out there that we have to deal with. So we have centrifugal force, which is counteracting the gravitational force and holding the tether very tight and taut. But is this system stable? So we can imagine deploying it so that it's vertical up and down with respect to the Earth. But what happens if you knock it from one side to the other? Well, it turns out that it naturally wants to orient itself to the vertical. And so the net force closer to the Earth is very strongly inward. And there's a radial component that points to the Earth. As you go further out, there's a net force slightly outward. And the result of these forces is that the cable wants to orient itself vertically all the time. And so it's naturally stable. We call this gravitational gradient stabilization. So it's the basis of keeping the space elevator in place without any thrust or other corrections. So we have major requirements that we need before we actually build a space elevator. The tether materials, of course. We have to spend some time on designing the climber, and we'll hear a lot about that in following talks. And then how are we going to power this climber? So let's talk about the materials. There are probably at least 4. Of course, the carbon nanotubes were the first ones available, and they are easily strong enough to make a tether. This is a single-walled carbon nanotube. Many of them have several walls, but this would be the lightest one. And then there is single crystal graphene. So this is effectively a 2D material. It has also a very strong strength. And a more recent addition to the list of materials is single crystal hexagonal boron. It looks just like graphene. It has the hexagonal pattern, except it has alternating carbon and nitrogen atoms. And then you could also make a nanotube out of the boron nitride. So these four materials are very good candidates for making a tether. The climbers could be a lot of different things to do. So one of the things that we look at first, of course, is can we make a climber based on friction? And that depends, of course, on what the properties of the tether are. Is it sticky or slippery? How well can a climber or a tether dissipate the heat of the friction? So you're going to be grabbing on and transferring some energy, and it will have to be dissipated, otherwise you could burn up the tether. Traction is an important thing, so are we going to have a contact drive, that is something that grips the cable, or a contactless drive? If we do have a contact, then we're going to have two choices. We're going to either have to deform the wheel that grips the tether or deform the tether. And you see these options listed over on the upper right. Another option, of course, is if we go to the contactless method, and then we'll have the so-called maglev technology. So we need to run, for example, a strong current through the tether, and this would create an intense magnetic field for the climber to push against. This is a nice solution because you don't have to worry about friction anymore. There are some other problems with this technology, but it is an option. And then at the bottom, you see a possible capstan climber design that was in, I believe, Brad Edwards' original book on the space elevator. Powering the climber is also a big deal, and we actually have a study going on in the Space Elevator Consortium on just this issue. So laser beaming to photovoltaic array, and on the right you see a picture of an actual climber from the 2009 competition, and there is power being beamed up to the purple area there where you see photocells, and that was powering the climber upward. There are problems to be dealt with. There's beam divergence, hazard to aviation and satellites. All of these things have to be dealt with. Another way to do it would be to think of power line transmission. So graphene, for example, is a very, very good conductor, and it has it supports high current densities. It might even be a superconductor if it's built in the right way. And so you could think of having power sent through the climber itself, or the tether itself, and then tapped off by the climber. You could also think of having a separate power line, sort of like an umbilical cord to a rocket, which falls away after the initial acceleration. And another very interesting idea is acoustic power transmission through the tether. So you could vibrate the tether at certain frequencies and have a kind of a transducer on the climber, which collects this power and transmits that into rotating wheels or other methods of propulsion. So that's an interesting one that we haven't really worked on very much, but it's something to consider for the future. So some challenges. What's very interesting about the latest work on space elevators is that we have the necessary materials. They exist, they have existed for some time now. What we really need is large-scale manufacturing. So pieces in the lab are of order centimeters, 10 centimeters, sometimes as half a meter long. But we really need to make kilometer-long lengths, and some companies are starting to do that. The climber drive options are also being worked on. Deployment is a very interesting thing, and that's being worked on. I'll talk about that on the next page. And of course, orbital debris. okay? Satellites, of course, can be tracked. We can avoid them. We can manage the orbits. We can cause the space elevator tether to move to avoid the satellites. But we won't be able to see or track everything. There will be some small micrometeorites and other space garbage and things like that. So some tether damage will be unavoidable. We'll have to assume that we're going to do repair and replace of the tether. And we estimate that that repair and replacement will probably take place on the order of every 10 years. Radiation is a problem. As I mentioned earlier, the end of the space elevator goes beyond the bow shock of the Earth, so it's in direct solar radiation. This can be mitigated by shielding, but that shielding is usually quite heavy, and that would cut down your payload quite a bit. So that's a challenge that has to be worked on. Atmospheric effects are another big one. So the climber, for example, would have to have an aerodynamic shroud when it goes through the atmosphere. You have to worry about things like lightning. Wind is another problem. That could put a severe load on the tether. So these calculations are being done, and we have an idea of what these stresses are, but all challenges and solutions to the challenges are being found. So here's a typical deployment scenario. One way to look at it is how you would build a long suspension bridge. The way it's done is that a cable is shot across the place where you want to put the bridge, just a thin rope or something like that. And then that cable supports other cables, and you keep building up until you get something which is enough to support a bridge deck or something like that. And so in space elevators as well, you would start with a pilot ribbon. And this could be, let's say, 20 to 40 metric tons in weight. Not very wide, 15 centimeters, but very long, 100,000 kilometers. So send up a coil of this tether material to geosynchronous orbit and start deploying the ribbon downward. As you do this, you're going to have to move the rest of the apparatus upward. You want to maintain the center of gravity and therefore the orbital position so that it's always over the same spot on the Earth. And then once the final or the initial pilot tether is anchored, you can start adding new tether material by assembly climbers, which would be small robotic climbers which add tether material. And it's estimated that after the first tether is put up, a more robust space elevator tether could be built with about 70 trips of the climber up and down the tether. Here's a picture of the space radiation environment. So in the center, of course, is the Earth, and the red lines represent the Earth's magnetosphere. The green line is the space elevator. So it extends beyond the bow shock. And now out at the end, you're going to have to deal with solar protons and fairly intense radiation. Only down at very low altitudes, low Earth orbit, are you going to be in a pretty safe radiation field. But almost immediately as you climb, you get into the Van Allen belts, and radiation is definitely something that you're going to have to deal with. So what is the first space elevator going to be like? Well, we already think it's going to be about 100,000 kilometers long. So this would be a tether of about 1,000 megatons, 400 megaton apex anchor. So this is a counterweight basically at the far end. You could make the tether longer and have a smaller counterweight, or you could make the counterweight bigger and a shorter tether. That's a design choice. The tether itself should probably be tapered. And so if you have what we call a constant stress model, that is, the stress throughout the entire tether is always the same, then it will have to vary. It will be its thickest at geosynchronous altitude and then get thinner again as it goes up in altitude, but the width will probably vary between 1 and 6 meters along its length. We think that it could support 20 metric ton climbers. And optimistically speaking, we think maybe that could be a 13 metric ton payload. So the rest of the other 7 tons would be machinery, things like that, radiation shielding. And we estimate 7 or 8 days to get to geosynchronous orbit. So it's a long journey, but if it's freight, that's not a problem. If it's humans, then there might be an issue that you have to supply living area for people who want to go in this direction. Now, there was an estimate about the costs. The first elevator probably could deliver mass to geosynchronous orbit at the rate of $3,000 per kilogram. By the time you've built, let's say, the 5th elevator, costs start coming down exponentially and might go as low as $300 per kilogram or so. So those are just rough estimates, but that might give you an idea of the costs if you want to compare to the costs of launching things in present-day rockets. And we think that as soon as we can get factories to produce large amounts of the tether material, that probably 20 years from that date, the first operational space elevator would exist. And so, yes, as soon as we convince some factories to start working, it could happen pretty soon. And that's all I have. I'd like to make an advertisement for the International Space Elevator Consortium. We fund research into space elevator development and contribute to research projects. One of our main goals is to spread the word that the space elevator is actually closer than you think. It's no longer science fiction. It's a serious engineering problem that people are working on. We will help, and you will help, to develop a transportation infrastructure that's going to really enable space enterprise for the future. And we ultimately hope to promote a spacefaring civilization. So if you're interested, go to www.isec.org. You can join, you can become a member if you want, or you could just look over the website and look at all the information that is stored there. And so that concludes my talk, and I believe I can open it up for questions.